This week we're going to look at Single Area Ospf protocol. Ospf is Open Shortest Path First, and it is a linked state routing protocol. It was developed to replace RIP, and RIP was acceptable routing protocol in the earlier days of networking and the internet, but it's become somewhat obsolete and problematic. So we're looking now at Ospf, or Open Shortest Path First. It is a classless routing protocol that uses the concept of areas for scalability. So we're going to look at just the single area Ospf implementation and configuration this week. There are two versions currently of Ospf. Ospf version 2 is available with IPv4, and Ospf version 3 is available for IPv6. And again, they are both interior gateway protocols, and they are link state protocols. Also, while I'm referring to Ospf, if I do not state version 2 or version 3, I am going to be talking about the properties that both versions have in common. Let's look at some of the features of Ospf. It is a classless protocol, and since it is classless, it supports VLSM and CIDR. It is efficient. The routing changes trigger routing updates. They're not periodic updates, so it's not set at an interval that, let's say, every 30 seconds or so that it updates. It's only going to update when that update is needed, and that's more efficient for your system because it requires less network traffic. It uses the shortest path first algorithm to choose its best path. There is fast convergence. It quickly propagates network changes. It's scalable. It works well in small and large network sizes. The routers can be grouped into areas to support a hierarchical system, and it's also considered secure. It supports message digest 5 or MD5 authentication, and when enabled, your Ospf routers only accept encrypted routing updates from peers with the same pre-shared password. The administrative distance is the trustworthiness or the preference of the route source, and Ospf has a default administrative distance of 110. One of the things that you can look at when you're looking at your different protocols, you'll notice the administrative distance. Here it says Ospf is 110. You can kind of determine which protocol or routing source is being used based off the administrative distance that it gives. There are three main components of Ospf routing protocols. They include data structures, routing protocol messages, and algorithms. With your data structure, it creates and maintains three databases. You have your adjacency database, you have your linked state database, and your forwarding database. The adjacency database is your neighbor table. And you can do show IP Ospf neighbor. It's going to show who your neighbors are. It lists all the neighbor routers to which a router has established bidirectional communication, and it is unique for each router. You have your linked state database. It's a topology table, and it lists information about all other routers in the network. If you do the show IP Ospf database command, you're going to get this information. Then you have your forwarding database, or basically your routing table. It lists of routers generated when an algorithm is run on the linked state database. And each router's routing table is unique and contains information on how and where to send packets to other routers. And we get this when we do our show IP route command. The Ospf routers exchange packets in a particular order. They do the hello packet. Then you have a database description packet. Then you have your linked state request packets. Then you have a linked state update packet, and then the linked state acknowledgement packets. And these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about your network, because you could possibly have a router go down, so this information needs to stay up to date. With your algorithm, you have a CPU process It processes the neighbor and topology tables using the Dijkstra's, I can't even say that word, shortest path first algorithm, and it's based on the cumulative cost to reach a destination. So the SPF algorithm creates your SPF tree by placing each router on the root of the tree and calculating the shortest path to each node. So to maintain the routing information, your OSPF routers complete the following generic link state routing process to reach a state of convergence. Okay. First, it establishes your neighbor adjacency, and that basically means who am I physically connected to, who's my neighbor. Then it exchanges link state advertisements, and this is done after the adjacencies are established, and routers then exchange link state advertisements. And then the link state advertisements contain the state and cost of each directly connected link. Then the routers are going to flood their LSAs to adjacent neighbors, and then your adjacent neighbors receiving the LSA immediately flood the LSA to other receiving. So it just kind of keeps passing things along. It builds the topology table, and then it executes the SPF algorithm, and then the content, it has all that information. So basically here in this diagram, we started out where we're going through and we are looking and establishing our neighbors. So router 1 is connected directly to router 2, 3, and 4. 2 is directly connected to 1 and 5. 3 is directly connected to 1 and 4. And 4 is directly connected to 1, 3, and 5. So it goes through its different processes. It floods out the LSAs. It builds its routing table. It calculates the shortest paths. It creates the shortest path first tree. In this instance here, they're talking about router 1. And then you have the content of what's the shortest path. You'll notice that the shortest path in this particular one is going to go from router 1 to router 3. It has a shortest path of 7. And here for router 1 to router 2, it is the longest at 30. Okay? To make OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. Now, this unit we're going to look at single area OSPFs. That's where all routers are in the one area called the backbone area, or area 0 in this instance. Or you can have multi-area OSPFs, and that's implemented using multiple areas in a hierarchical fashion, and all areas must connect to the backbone. So routers interconnecting the areas are referred to as area border routers. With multi-area OSPF, it can divide one large autonomous system into smaller areas to support hierarchical routing. And with hierarchical routing, routing still occurs between the areas because you have inter-area routing, while many of the processor-intensive routing operations, such as regulating the database, are kept within an area. So it's not looking outside of where it needs to go. The hierarchical topology possibilities of multi-area OSPFs have some advantages, and they are: you have a smaller routing table, you have a reduced link state update overhead, and you've reduced frequency of shortest path first calculations. Now, OSPF has different messages that are transmitted over your Ethernet link, and they contain the following information. You have your data link frame header, you have your IP packet header, you have your OSPF packet header, and your OSPF packet type specific data. In the data link frame header, you have your MAC address and your MAC source addressing. In the IP packet, you have your IP source address and your IP destination address. You notice it also has the protocol field. Then the OSPF packet header is the type code for OSPF packet type, your router, and your area ID. And then the OSPF packet types, you have hello, your database description, your link state request, your link state update, and your link state acknowledgement. Now, OSPF uses link state packets, the LSPs you will see them referred to establish and maintain neighbor adjacency and exchange routing updates. In the figure here, it shows you the different types. Type 1, we have hello, that discovers your neighbors and builds adjacencies between them. Then you have database description. It checks for database synchronization between your routers. Link state request, or the LSR, requests specific link state records from router to router. Then we have link state update. That sends specifically requested link state records. And we have link state acknowledgement, which acknowledges the other packet types. Now, let's talk a little bit about the hello packet. With the hello packet, it is type 1, like I mentioned a moment ago, and they're used to discover your OSPF neighbor and establish neighbor adjacencies. It kind of goes, hello, who's out there, and then we get our responses back. But with the hello packet, it advertises parameters on which two routers must agree to become neighbors. Okay, so they have to agree to become neighbors. They elect the designated router, or the DR, and the backup designated router on multi-access networks like Ethernet and frame relay. With point-to-point links, they do not require a designated router and a backup designated router. Here is an example of a type 1 hello packet with some of the important fields shown. You have the type, that it identifies the type of the packet as a 1. That is right here. It's a hello packet. You have your router ID. You have your area ID. Then you have your network mask, and that's the subnet mask associated with the sending interface. You have your hello interval, and that specifies the frequency in seconds at which a router sends a hello packet out. The default hello interval on multi-access networks is every 10 seconds. And this timer must be the same on neighboring routers, otherwise the adjacency is not going to be established. They're not talking at the same rate. You have your router priority, and that is used with the DR BDR election. You have your dead interval, and it's the time in seconds that a router waits to hear back from its neighbor before declaring that the neighbor router is out of service. That's how it knows when a router has gone offline. If it hasn't heard back from it in a certain amount of time, then it assumes it's dead. It goes to its backup. If it doesn't hear back from it, then it moves on and it drops that link. Our next type is type 2. And routers initially exchange type 2 DBD packets, which is an abbreviated list of sending routers, LSDBs. Type 3 LSR packet is used for receiving routers to request more information. The type 4 LSU packet is used to reply to the LSR packets, and also used to forward OSPF routing updates such as link changes. Specifically, an LSU packet can contain 11 different types of OSPF on version 2 LSAs, and version 3 has renamed several of these LSAs and also contain 2 additional LSAs. So some of these have changed up just a bit. Alright, now let's look at transitioning through our OSPF states. When the OSPF router initially is connected to a network, it attempts to create its adjacencies with its neighbors, looks to see who's out there. It exchanges the routing information, it calculates its best routes, and then it reaches convergence. And all this happens rather quickly. OSPF progresses through several states while attempting to reach convergence. You have your down state, your initial state, you have a two-way state, you have the X start state, an exchange state, loading state, and full state. Okay? To understand what each of these are, when you go through your ebook, you can click on each of them. Here it says the down state. There's no hello packets received. It's down. The router sends hello packets, and it transitions into the intent state. Here we have the hello packets are received from the neighbors. They contain the sending router's router ID, and it transitions to your two-way state. So here on the Ethernet links, it elects the DR and the BDR, and it transitions to the X start state. At that point, we negotiate our master and our slave relationship and the DBD packet sequence number, and the master initiates the DBD packet exchange. Then our routers exchange DBD packets. If additional router information is required, then transition to loading. Otherwise, the transition is full. Then you have your LSRs, and then your LSUs are used to gain additional route information. Your routes are processed using the SPF algorithm and transition to the full state. Once we're at a full state, your routers have now converged. But this happens very quickly on our systems. Okay, with OSPF is enabled on an interface. So you're using the OSPF protocol. The router must determine if there is another OSPF neighbor on the link. And to accomplish this, the router forwards your hello packet, and it's the OSPF hello packet that contains the router ID out all OSPF enabled interfaces. So you enable OSPF per interface. The OSPF router ID is used by the OSPF process, and it is able to uniquely identify each router in the OSPF route area. The router ID is an IP address assigned to identify a specific router among the OSPF peers. When a neighboring OSPF enabled router receives that hello packet with your router ID that is not within a neighbor's list, then that receiving router attempts to establish an adjacency with the initiating router. It says, hey, I didn't know about you. Let's see if we become neighbors now. The action performed in a two-way state depends on the type of interconnection between the adjacent routers. If the two adjacent neighbors are interconnected over a point-to-point link, then they immediately transition from the two-way state to a database synchronization phase. If the routers are interconnected over a common Ethernet network, then the designated router and the backup designated router must be elected. So then you have to have an election process. And this election process only occurs on multi-access networks such as an Ethernet LAN. And you may wonder why you have to have an election. Why is a designated router and a backup designated router necessary? With multi-access networks, you can create two challenges for OSPF regarding flooding of the LSAs. You have the creation of the multi-adjacencies, and that's where the Ethernet networks can potentially interconnect many OSPF routers over a common link. That creates adjacencies with every router. It's unnecessary and undesirable. It would lead to an excessive number of LSA exchanges between routers on the same network. So you just have all kinds of stuff going on. You have extensive flooding of LSAs. That's when the link state routers flood their LSAs anytime OSPF is initialized, or when there is a change in the topology. And this flooding can become excessive. So you can look at it in a couple of different ways. For any number of routers designated here in our formula as an end on a multi-access network, there are n times n minus 1 divided by 2 adjacencies. Okay? So in this example here, you see all of our adjacencies. We have all these routers and we have our switch. Okay? So n is the number of routers. So n times n minus 1 divided by 2. Okay? You do the math. So n is 5. N minus 1 is 4. So 4 times 5 is 20 divided by 2 is 10. Okay? In that one, that's not too many adjacencies. But look what happens if you have 20 routers or even 100 routers. The number of adjacencies that can occur. So the solution For managing the number of adjacencies and the flooding of the LSAs, just think about it, how many, if you had 20 routers, how many adjacencies that would be. The multi-access network is the designated router. On your multi-access networks, Ospf elects your designated router to be the collection and distribution point for LSAs sent and received. Then you have your backup designated router. It's also elected in case the designated router fails. All other routers become druthers, basically. A druther is a router that is neither a designated router or the backup designated router. So let's see how we go about deciding which router sends the first DBD. After the two-way state, routers transition to the database synchronization state, and while the hello packet was used to establish neighbor adjacencies, the other four types of Ospf packets are used during the process of exchanging and synchronizing the LSDBs. In the X state, a master and slave relationship is created between each router and its adjacent designated router and backup designated router. The router with the higher router ID acts as the master for the exchange state. In the exchange state, the master and slave routers exchange one or more DBD packets, and it includes information about the LSA entry header and appears in the router's LSDB. The entries can be about a link or about a network. Each LSA entry header includes information about that link state type and the address of the advertising router. The link's cost and sequence number. The router uses the sequence number to determine the newness of the received link state's information. After all LSRs have been satisfied for a given router, the adjacent routers are considered synchronized and in full state. As long as the neighboring routers continue receiving hello packets, the network is in the transmitted LSAs remain in the topology database. After the topological databases are synchronized, your update LSUs are sent only to neighbors when a change is perceived and every 30 minutes.